Hello, class. I'll be right back. I'm going to get some coffee. Okay. I'll wait about 30 more seconds for more people to join. Everyone's doing well. Okay, I think I'm going to start. Okay. Focus. Boom! Okay, we're ready. So what I'm going to talk about for the next two lessons are musical instruments. That is what we are going to talk about. Okay. So let's just start off by just talking about musical instruments a little bit. This doesn't really have to do with physics, but you know, I might mention some of these words later on. So, okay, so let's just see. Let's draw a piano. What does a piano look like? Do you have a picture of a piano in your head? So let's say this is a piano. Okay. So it kind of looks like this. Wow, this is a horrible looking piano. So I'm only going to draw that much of it. Okay. Boom. Go like this, 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 this. Oh man, I messed this up completely. Now I have to start over. Oh my gosh. I'm embarrassed. Can't believe I messed that up. Okay. There we go. Okay. Now this is what a piano looks like. Okay. So Here's our piano. Pianos have black keys and white keys. Okay. And you can see that the black keys are grouped into 2 black keys, and then there's a group of 3 black keys. Then there's a group of 2, and then a group of 3, and the pattern repeats. Okay. So if you look at the the group of 2 black keys, the one that's just to the left of that, that is a C note. Okay. And then you just go up the alphabet. C, D, E, F, G. And then the, okay. And then it starts over at A. So A, B, and then look at, we're back to a C. I know that this is a C because there's a group of 2 black keys, and then I'm just to the left of that. Okay. Now the black keys are sort of in between a C and a D. So this black key is called, so this is called a full step. Okay, full step. And then if you only go up between, that's called a half step. Okay, and if you go up a half step, that's called sharp. So this is C sharp. Okay. Alternatively, if you go down a half step, that's called a flat. So this is C sharp is also D flat. Okay. And similarly, this would be D sharp. This would be F sharp, which is also G flat, and so on. So you have all these keys. Okay. So if we go from one C to the next C, that is called an octave. Okay. And so that's a very important musical interval. If you go from a C to a G, because it's 5 keys, that's called a fifth. If you go from a C to an F, that's 4 keys over, so that's called a fourth. C to E is a third, etc. Octave, octo means 8, so there's 8 keys here. All right. So it's important to understand that the note in music is really just the same thing as frequency in hertz. Okay? So if I gave you a sequence of notes, like first play C, then play E, then play G, or something, really I'm saying make one frequency, then make another frequency, then make another frequency. Okay? So notes are really just frequencies of sound waves. Okay? And there are, and as you go to the right on the piano, you are going to higher frequencies. Okay. 1 octave. Now this is important. Okay. So if I want to know what is the frequency of a C 1 octave higher, okay, it is twice the frequency of the previous C note. Okay, so in other words, the frequency that this C is twice the frequency of that one, because this C is 1 octave above. Okay, So whenever you go up 1 octave, you double the frequency, okay? Now, how many steps do we go up in music to get to the next octave? Well, you go 1, including the black keys. So you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So basically, 1 octave is equal to 12 half steps. Okay? 1 octave is equal to 12 half steps. All right, and we know that 1 octave is the frequency times 2. Okay, so it actually turns out that a half step is going to be the frequency times 2 to the 1/12th power, because there are 12 half steps. All right, so for example, I happen to know that A, the note A, is 440 hertz. This is concert A. So if you ever go to a classical music concert, all right, you ever go to a classical music concert, there will be a person who comes out to the front of the orchestra, and they'll go, and then everyone else tunes their instrument to that note. They'll go, and then everyone goes, everyone tunes it, and that note is 440 hertz. That's an A. Okay? So what if I wanted to know what is the frequency of A sharp, which is a half step up? Well, then A sharp would be 2 to the 1/12th times 440 hertz, because it's a half step up from that. Okay? So if I do 2 to the 1/12th power times 440, I get 466 hertz. All right? And similarly, if I wanted to go from A to B is 2 half steps, because I go from A sharp and then to B. Okay? So 2 half steps. So a B is going to be 2 to the 1/12th squared times 440, because it's 2 half steps. Okay? So 2 to the 1/12th, 2, and that is 494 hertz. Okay? So my point is that, because I know many of you are into guitar, into music, maybe you're in choir, maybe you're in guitar class with Mr. Mellinson, maybe you're in band, many of you are interested in music. So the point I want to make is that the note that you think of in music is simply frequency, okay? And there's a definite relationship between these musical intervals that you're used to seeing, like an octave is twice the frequency. So if this is the 440 hertz A, then the next A is 880 hertz. It's double the frequency. Okay? And the next A is 1760 hertz. Okay, so every time you go up, you multiply by 2. And if you go up just a half step, it's multiplying by 2 to the 1/12th power. Okay? I could say a lot more about that, but I will shut up, and we'll get to the physics part, because this isn't really physics. I just wanted to sort of introduce music as really just frequencies, okay? Well, maybe I'll talk a little bit more about piano. So if you've ever looked at the inside of a piano, okay, like a grand piano, it has strings, okay? And when you push the key on the piano, ding, it brings up a hammer from underneath the string. So here's the string, and then the hammer comes up and goes thunk and hits the string and causes it to vibrate. So pianos are actually percussion instruments because it is a mallet that hits the string and causes it to vibrate, okay? So today what we're going to be doing is we are going to be talking about stringed instruments. Which, for examples of stringed instruments include pianos. And like I said, it doesn't look like a stringed instrument, but the internal mechanism, it's a string. That's what I like to play. I like piano. And then, violins, cellos, guitars. So all of these are, of course, stringed instruments, okay? And so basically what a stringed instrument is, if we get right down to it, is a string that is attached at two ends. Okay. Okay. And so an instrument could, of course, have multiple strings. Okay. So piano has lots and lots of strings. Guitar has 6 strings. A violin, I think, has 4 strings. I'm not sure on that. Cello has 4 strings. So that we're just going to look at one of those strings on that instrument. And typically that string is a certain length. So there's a length from where the string starts to where the string is fixed again. And so we will call that length L. So L is the length of the string. Okay. So when you pluck a string, or when you bow a string, or what have you, you create what is called a standing wave. Okay? As opposed to a traveling wave. So you have standing waves and you have traveling waves. So I'm speaking right now. It's a traveling wave. That sound wave is going out, okay, and it's never coming back. But if you have a wave in a confined space, like on a guitar string, right, this wave is confined. If I pluck the string, the wave bounces back and forth along the guitar string. It's stuck in place. So we call that a standing wave, like it's standing still, okay? We can also have a standing wave in a bathtub. If you're in the bathtub and the water is sloshing around, the water is stuck within the confines of the bathtub, so that is a standing wave. But if you make a splash in the ocean, the wave just travels. It goes away and it never comes back, okay? So that's so we have standing waves and we have traveling waves. Okay. Standing waves can only have certain wavelengths. standing waves can only have certain wavelengths. So why do I say that? Well, because at the boundary of the instrument, the string is fixed. Okay? So imagine you pluck this string. It's going to vibrate. Probably the vibration is going to look something like this. It depends on the way you pluck it, but it's going to go up for half the time. It's going to kind of go boing, 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 boing. Okay? And then it's going to go down for half the time. So you can see that the ends of the string never move because they're stuck. Okay? So standing waves can only have certain wavelengths. All right? So let's draw. What are the possible standing waves that can exist on a string? Okay? So I'm going to draw this one again. So I have, and I'm going to draw the equilibrium position of the string as just a straight line. So you can have the wave where it goes up and then it goes down. Okay. You could have, so the wave is going like this. All right, that's an example of a standing wave. You could have a wave that looks like this. Okay. And then the other half of the time it looks like this. So it's kind of going. Really need to get a slinky so I can demonstrate for you. Okay, so that is a wave. And then another wave you can have has 3 bumps. Like this. Okay. So notice how all these waves are pinned at each end, so they don't vibrate at the ends. Okay, they're vibrating here, they're vibrating here, they're vibrating here, but they're not vibrating at the ends. The next wave I can draw is this one. Okay, and then I'll do one more. So let's see. It's kind of hard to draw these. Okay, so there's obviously a pattern here. Okay, we can see. I like to think about this vibration of the string like this as like a football. To me, that looks like a football. Okay, so if we go from one picture to the next, okay, basically we add a football. Okay, so you can see that this has one football. Okay, this has one football. This has 2 footballs that are like tip to tip. This has 3 footballs that are tip to tip to tip. 4 footballs, 5 footballs. So every time we go up, we add a, quote, football. Okay. So the number of footballs in the standing wave is called the harmonic. The harmonic number, which is denoted by n. So this is harmonic 1 because it has 1 football. This is harmonic 2 because it has 2 footballs. This is harmonic 3 because it has 3 footballs. This is harmonic 4, harmonic 5, and it continues. Okay? So we'll talk about the nth harmonic, the first harmonic, the second harmonic, the third harmonic, etc. Okay? So now what I would like to do is I would like to talk about what is the wavelength of each harmonic. Okay? And so we're going to try to get a pattern. Okay? So the thing about a wave, if we have a full wave has a peak and a valley. Okay? This wave just has a peak. See how it only arcs up? Or it just has a valley. But it never has both at the same time. Okay? It goes from peak to valley, to peak to valley. So if we wanted to have a full wave, we would have to add a valley. Now the valley has the same size as the peak, right? So if the length of the instrument is L, the wavelength is a peak and a valley, so that wavelength is 2L. So the wavelength of the first harmonic is 2L. Okay? The wavelength of the first harmonic is 2L. And I'm going to write that in the suggestive form of 2L over 1. Okay? If we look at the second harmonic has a peak and it has a valley. A peak and a valley. All right? So this is a full wave. All right? So, and it looks like a full wave is exactly the length of the instrument. So the wavelength of the second harmonic is just L. But I'm going to write that as in a more suggestive form so that you can pick up on the pattern. 2L over 2. Okay? If I look at the third harmonic, okay, I can see that from here to here is a full wave. All right, because this is where a peak and a valley are. And I can see that that's 2/3 of the way across the instrument because each football has the same size. Okay, this football is the same size as that football is the same size as that football. So this is 2/3 of the way across the instrument. And the entire instrument has length L. So the wavelength of the third harmonic is 2L over 3. Okay, now let's look at the fourth harmonic. This would be a full wave because that is a peak and a valley. And so because there are 4 footballs, this is half the length of the instrument. So the wavelength of the fourth harmonic is L over 2. But I'm going to write that in the more suggestive way of 2L over 4. Okay? If I look at the fifth harmonic, I can see I have a peak and a valley. So this distance right here is a full wave. That's the wavelength. And I can see that there are 5 footballs, and this is 2 of them. So a full wavelength is 2/5 of the length of the instrument. So the fifth harmonic, it's 2L over 5 is its wavelength. So I think you can guess that the wavelength of the nth harmonic is 2L over N. Okay? 2L over N is the wavelength of the nth harmonic. Okay? So now let's talk about frequency. All right? So the formula for frequency, if I look at the equation V equals lambda F, I can solve for frequency. Frequency is V over lambda. Each harmonic has its own frequency, okay? And I can calculate that frequency by plugging in this formula for the wavelength. All right? So the frequency of the nth harmonic is equal to V over lambda. So it's NV over 2L. So again, I just plugged in this formula for the wavelength into there, and I get the frequency of the nth harmonic. All right? So this velocity is the speed of a wave on the string. Okay? And this L is the length of the vibrating portion of the string. Okay? So I'm going to grab my ukulele. Give me 1 second. Okay, so I have a ukulele right here. Okay. Okay, so it's approximately in tune. Okay. So if I look at this, if I play a note on the ukulele, okay, if I play a note on the ukulele, the vibrating portion of the string is from my finger to this part. I don't even know what that part's called, but from my finger to that part. All right? Notice how, what if I shift my finger up the fretboard so that now the vibrating portion of the string is only here? That's less vibrating portion. The length of the vibrating portion of the string is smaller. Okay? So we can see that as the length of the vibrating portion of the string got shorter, the frequency went up. Okay? It went to a higher pitch. And sure enough, look at this equation. As the length gets smaller, the denominator of the fraction gets smaller, so the frequency goes up. Okay? So basically what you're doing when you're playing a stringed instrument is you're adjusting the length of the string with your finger to get the right frequency. Okay? Now the bridge. Thank you. Now the other thing that we have control over is the wave speed, V. Okay? So I have these pegs up at the top of the ukulele, which are for tuning it. Okay? So I'm letting the full string vibrate. And if I turn the peg, so So I'm plucking the string in the exact same way every time, but because I'm changing the tension in the string, I'm adjusting the wave speed, which changes the frequency that it plays. So, and then of course the different strings have different thicknesses, okay? And they can be made out of different materials, so that also affects the wave speed, okay? So the wave speed is affected by the tension and the thickness and the material of the string. And then once we've set that, the length of the vibrating portion of the string is what determines the frequency and hence the note. Okay? So I got that way out of tune. Let me get it back in tune. Okay. So anyways, that's a little bit about it. So what I wanted to, so I have a couple more things to talk about. So when you pluck a string, when you pluck a string or bow a string or whatever, you create a superposition of all the harmonics. Okay. So when you pluck a string, when I do this, I'm creating a little bit of the first harmonic, a little bit of the second harmonic, a little bit of the third harmonic, all of them. Okay. But the thing is that they all have different amplitudes. They all have different amplitudes. Okay? And usually the first harmonic has the biggest amplitude. Okay? So basically, we hear the first harmonic. As far as tonality is concerned. So if the first harmonic is a C note, the second harmonic is not going to be a C note. But we don't hear the second harmonic as strongly as the first harmonic. Okay? So we're just going to hear a C note. So we hear the first harmonic. So when you pluck a string, you are going to hear the frequency that you hear is the one with n equals 1, which is just V over 2L. Okay? That's the one you're going to actually hear. The higher harmonics give the sound its uniqueness, its timbre is what we would say. Okay, so if you think about it, I could la la. I am singing the same note as the guitar. La 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 but you can tell me apart from the ukulele. Why do I sound different from the ukulele? We're both singing the same note. We're both have the same first harmonic, but the other harmonics are different. Okay, maybe I have extra second harmonic in my voice compared to the ukulele. So that's going to give my voice a different quality from the ukulele. Okay? So the higher harmonics are what give sound its unique character for a particular instrument. All right. One last thing I wanted to talk about Um, so if we think about this string vibrating, this portion of the string vibrates a lot, whereas this portion of the string doesn't vibrate at all, right? Because it's kind of like in between a peak and a valley, so it's just always fixed. So that those points on the wave that are always fixed are called nodes, N-O-D-E-S. And the points that are always moving are called antinodes. Okay, so we can see that this wave right here, the third harmonic, or the second harmonic, excuse me, has 3 nodes, 1, 2, 3, and 2 antinodes. The third harmonic has 1, 2, 3, 4 nodes, and 1, 2, 3 antinodes. Okay, so you'll hear that term sometimes, nodes and antinodes. Every stringed instrument has at least 2 nodes because the 2 ends are fixed. They can't vibrate. Okay. So that is my lesson for today. And I will see you in the Zoom room for further discussion. Bye-bye.